All right, segment of section 9. We are now going to look at multiple regression. It is an extension of the end of the last section where we talked about simple linear regression. Now we're going to be using more than one independent variable in an attempt to more accurately predict the dependent variables. We're going to start with the same example problem that we had in the last section, where we have this survey that was done asking people about their opinion of Springdale Mall. And we're going to continue the same type of discussion about how important each one of these independent characteristics are on the overall attitude towards Springdale Mall. So let me pull this over here. Here's where we left off in section 8 with a simple linear regression where we were using a single variable take fam, and we found that it described a very small portion of the variance in the attitude, or the characteristic of attitude. So now we're going to include more than just one variable in our regression. So we go to data analysis. We've done this before. We're going to be using the tool regression. The y, or dependent variable, will remain the same, so I'm not going to do anything with the dependent variable. The independent variables, however, I'm going to include all 4 of these independent variables. So we have take, fam, variety, convenience, sex, or gender. I'm going to allow this to move on to another worksheet. Now you'll notice that the x variables, or the independent variables, have to be congruent. They have to be next to each other in Excel, because I can't just pick one column or another. I've got to pick all the columns together. So before you run the regression, you'll have to move the variables around to make sure that those independent variables are next to each other. Okay. So here is our output. Now our R squared has gone up considerably. It's gone up from, I think it was 1.2% to almost 15% by adding these additional variables. And our adjusted R squared has increased as well. So we can see that there is value, there is predictive ability in these variables that we've added. Now let's talk about each one of those. So you'll see that this is the output that we received. We're going to focus once again, as we did before, on the R squared and adjusted R squared. We'll speak just a little bit more on this value of significance F, because it's telling us more now than it did before. Before, it was the same as the p-value for the coefficient take fam, the single variable that we had in our model. Now it is this descriptive predictive ability. Is there statistically significant predictive ability in our model? Then we can look at each of the individual coefficients. And each of the individual coefficients will tell us something about the relationship, and we can look and see if it is statistically significant. So here's the output that we had from the previous section. So the first question is, how much of the variability in y does the model predict? How much of the change in attitude is predicted by the changes or variances in the other 4 variables? Now we're going to be looking at these not just on a one-to-one, but we'll be looking at the total explained variability. So the R squared is that percentage of variance in y explained by all, and I want to emphasize that word, all of the variables combined. So we see this all here, of the predictive variables. Does the model explain a significant amount of the variance? Well, there's a temptation here to look at the R squared and say, is the R squared high or is the R squared low? The R-squared really doesn't matter about the size. There's some disciplines where an R-squared of 5 or 10% is pretty good. Other disciplines where you require a 90, even a 95% R-squared. To explain the significant predictive variability of the model, we need to look more at the F-statistic. The F-statistic we've used before. It is the explained variability over the total or unexplained variability. And the significance F is going to tell us, is that explained variability significant? Have we explained a significant portion of that? We can think of that significant F variable much like the p-value that we've used before. The p-value says, what is the probability of getting this result if there truly was no relationship, or if this relationship was randomly selected? If the p-value, or the significance F, is less than our alpha, then we can say that this relationship is not from random or sample error, that there is a true correlation and there's this predictive relationship. So we use that kind of same rule. If the p-value is greater than alpha, we retain the null. The model isn't predicting our dependent variable. If the significance F is less than alpha, then we would reject the null hypothesis and say, yes, indeed, there is a predicting relationship. Number 2, what is the regression equation? Well, in the first section, in section 8, simple linear regression was just looking at an intercept and then a single slope. Now we're looking at multiple slopes. So if we only had 2 independent variables, we could kind of imagine that slope going into space. Kind of imagine it like this, where we've got our x1, y, and then we have this second x2. And the data here, I can't really draw it too well, is moving into space, and the slopes that we're looking at is that projection of that line into space onto those different planes. Now, that's not so important that you totally understand that. What's important is that you recognize that we can still use the same equation, but now we're just going to be adding these additional components. So what do these mean? Let's jump down to number 3. We'll come back to linear relationships in the advanced sections. Are the slopes significantly different than 0? We start with the assumption that the slope is equal to 0, that beta I, beta 1, 2, 3, 4, whatever the slope is equal to 0. If the t-statistic is less than 2 and the alpha is greater than 0.5, then we would fail to reject, or we'd have to retain the null. However, if the p-value is less than alpha, and we can use that kind of rule of thumb for the t-statistic being equal to 2, then we can reject the null, and we can say that the coefficient truly is something other than 0. Now, it may be positive or it may be negative, but we can say that the slope is statistically significant. That controlling for all other variables, there is a statistically significant relationship between each of those. So let's come back up here and assume that we have this regression equation. And we would say that the attitude starts when all other factors are 0 at a y-intercept of 2.65. For every unit of take fam that is increased, so if we go, for example, from a 2 to a 3 for take fam, we would see that the attitude would increase by 0.036 units of attitude. And similarly for variety, convenience, and then the gender. Now this is an interesting variable. This is a 0-1 variable, which tells us that one gender is valuing or has a higher attitude on average of about 0.018 units than the other gender. I think in this case females are 1 and males are 0, So on average, females have a higher attitude even after controlling for the other factors. Now let's interpret this equation. When we look at a simple linear regression, it's fairly easy to just say that there is this direct or indirect relationship. Now we have to start thinking about these things in interactive relationships, because asking a person, how do you think about the convenience, is almost or very similar to asking the person, how do you feel about the variety? So it's almost never possible to interpret the y-intercept simply as a predictive variables. The coefficients, let me go back. The coefficients are technically not slopes anymore, since there are more than one. They become much more difficult to interpret. It is no longer the influence of the predictive variables on y, but the effect of x after the effects of all of the other variables have been taken out. So it's kind of like saying, after controlling for all of these other elements, or holding all of these other elements constant, what is the, for example, true relationship between variety and attitude? The multicollinearity comes in because we have this overlap. Okay, multicollinearity we can see when we do our correlation matrix, and we can see that these independent variables are actually correlated. Ideally, we would want a situation where each of the variables are not correlated. So each of the variables independently describe attitude, and they don't describe any of the portion of attitude that's described by the other variables. This rarely happens. Now, how do we handle this multicollinearity? We'll discuss a little bit more in the future, but we need to recognize that there is this overlap. Almost always there's overlap, and we're going to be able to see that when we look at the regression.